life without glaciers. I am a glaciologist, and the first thing that people often say to me when I tell them that I'm a glaciologist is they say, not for long, not for long. So we've talked already about what a 1.5 degrees is maybe something that we can aspire to, but I want to think a little bit about what that might mean for the world's ice. And if we go beyond 1.5 degrees, what does that mean for a world potentially without ice? Let's think a little bit about how much glacier ice there is in the world. Now, there are two ice sheets in the world. There's the Antarctic ice sheet and there's the Greenland ice sheet. So here's Antarctica down at the South Pole and Greenland up at the North Pole. And those two ice sheets hold most of the world's fresh water. They hold enough fresh water to raise global sea levels by about 59 meters in Antarctica and about 7.5 meters in Greenland, an unimaginable amount of water. But there's another store of ice in the world, and that is the world's glaciers. Now, the world's glaciers have enough ice to raise global sea levels by a paltry 32 centimeters if they all melted. So the world's ice is only a tiny fragment of the world's ice is included in the world's glaciers. And these pie charts show us where those glaciers are in the world. So number 19 are the small glaciers around the fringes of the Antarctic Peninsula. Number 16, this tiny dot here, is the world's tropical glaciers. And we do have glaciers in Africa and in Peru and Colombia, tiny, tiny glaciers. Number 3 up here in the north, this is Arctic Canada. You can see the size of the circle is very large. And then we have a lot of ice in the Arctic. And also number 1 is Alaska. We have 13, 14, and 15, high mountain Asia, an important source of ice for local people, but not as significant in terms of global sea level rise. Worldwide, our glaciers are receding. This is Columbia Glacier in Alaska from 1986 to 2019. And Columbia Glacier is one example of a retreating glacier, but the signal is coherent. Almost all of the world's glaciers are shrinking. Each year, they are melting more than they are being replenished by snowfall. So there's more melt happening than snowfall happening every single year for almost all the glaciers worldwide. And all of this melting of ice is affecting sea level rise. Globally, our seas are rising at about 3 millimeters per year. And we've lost trillions of tons of ice over the last 20 or 30 years. This is from the Global Sea Level Budget Group, from a paper by someone called Tom Slater. And in pale blue here, we have the loss of the world's floating ice. So we have the Antarctic sea ice and the Arctic sea ice. That's the frozen seawater that freezes and unfreezes each year. You can see there's a big loss of Arctic sea ice. And then we have ice shelves. We've also lost these darker blue areas from ice shelves. And then these more indigo colors, these darker blue colors, this is from what we might call land ice. This is from ice above sea level. And if that ice goes into the sea, then it has a sea level contribution. So you can see on this axis on the other side, we have sea level contribution, and it's only for the world's land ice or grounded ice. So here in the middle, we have Antarctica. We've got an increasing contribution to global sea level rise from Antarctica, and again from Greenland. But the biggest source of global sea level rise is actually from the world's glaciers. Although they're only a tiny fraction of the world's global ice volume, they're contributing disproportionately to global sea level rise. And if we look at the pie chart, or the slices of pie that each part of the world's frozen system contributes to sea level rise, we can see that of that 3 millimeters, 24% of that is from the world's glaciers. Half of the sea level rise we see is from ocean thermal expansion, and of the half that's from land ice melt, almost half of that is from the global glaciers. And this is projected to grow and to increase. And we would expect to see global glaciers to dominate sea level rise at least until the year 2100. And it's not until we get really beyond the year 2300 that we start to see really significant dominations from places like Antarctica. This rate of ice loss has risen by 57% since the 1990s, and our world's glaciers are definitely in peril. This is the coherent signal of worldwide glacier recession. Each of these pie charts represents the volume of ice that has been lost from global glacier ice. So you can see this biggest circle here says 266.6 gigatons per year. 1 gigaton is a cubic kilometer of water. So it's a pile of water 1 kilometer wide, 1 kilometer high, and 1 kilometer deep. I'm not even going to try and give you that in terms of Olympic swimming pools. It is so many Olympic swimming pools. You could fit you could fit Ben Nevis or Mount Snowdon into this cubic kilometer of water. It takes 361 cubic kilometers of water, or 361 gigatons of water, to raise global sea levels by 1 millimeter. So even though a gigaton is a massive volume of water, the sea is really big. So 361 will raise global sea level by 1 millimeter. Globally, our glaciers are losing 266 gigatons of water every single year. Every single year. And that rate is increasing by about 48 gigatons or 48 billion tons of ice per decade. And that's contributing about 1/3 of a millimeter to global sea level rise every year. And you can see that the biggest source is from these glaciers in Alaska, 66 gigatons. But we also have losses from the glaciers around Antarctica, the Southern Andes, Arctic Canada, and Arctic Canada North. All of these places globally are melting more than they are growing. Every single region in the world the glaciers are shrinking, and we can see that unequivocally here. So are we headed towards a world without glaciers? We recently had COP26 in Glasgow, and in COP26, what the different countries try to do is make commitments, nationally determined contributions, commitments of how much carbon dioxide they're going to emit. These pathways here show how much carbon dioxide we need to emit. So we've got global greenhouse gas emissions on the y-axis. On the x-axis, we've got years. So we've got the different pathways of carbon dioxide that we need to emit in order to meet these different agreements. So the Paris Agreement, this is the pathway of greenhouse gas emissions needed to limit global warming to below 1.5 degrees centigrade. And then in dark blue, this is the pathway of greenhouse gas emissions needed to limit global warming to less than 2 degrees centigrade. And at COP26, this red line here, this red line is what was agreed at COP26 in terms of greenhouse gas emissions over the next 10 years to 2030. And you can see that we are far above the pathways needed to limit global warming to less than 1.5 degrees centigrade. And in fact, we're following a climate pathway that's called SSP 245. The 4.5 refers to the amount of watts per meter squared of warming that we get from putting greenhouse gases into the atmosphere. So if you see this, that's what that means, SSP 2.45. And I want you to remember that number, because we can run global models that tell us where the glaciers will be in the year 2100 if we follow that pathway, that SSP 245 pathway. So the SSP 1 19. This is the pathway that sees us limit warming to less than 1.5 degrees centigrade. That would see sea level rise projections from glaciers of 7 centimeters. If we go to SSP 126, we would see 8 centimeters sea level rise from glaciers, and SSP 245, we see 11 centimeters from global glaciers. We only have 32 centimeters of sea level rise equivalent in the world's glaciers. So if on our current trajectory, we will only have 1/3 of today's ice volume left. We'll have lost 1/3 of today's ice volume in the year 2100. That's where we are in line to be at the moment, as of the most recent climate change negotiations. And why is this important? We might think, well, I don't really care if the sea level rises by 3 millimeters a year. I stand on the beach and it goes in and out and in and out and it doesn't bother me. But then you remember, well, hang on, we've had some storms recently. And when we had those storms, we had an area of low pressure over the coast. We have strong winds driving the waves on shore, and suddenly we get coastal flooding. So when you have a higher sea level, the climatic conditions needed to flood the coast is less. And so you get more frequent floods around the coast. By the year 2100, if we take into account sea level from Antarctica and Greenland, we're looking at 25 centimeters of rise of global sea level just from land ice. And if we include thermal expansion of the ocean, under SSP 245, under that current scenario, we're looking at a sea that's 0.5 meter higher than it is today. And that means much more frequent coastal flooding. 680 million people worldwide, including large parts of the British population, live in low-lying coastal areas susceptible to flooding. Here is the Thames Barrier. We raise the Thames Barrier during storms to prevent London from flooding, to prevent these storm surges. And under these scenarios, the Thames Barrier would not be sufficient to protect London. It protects London currently against a 1 in 1,000 year flood. But if sea levels are 0.5 meter higher, then a 1 in 1,000 year flood becomes something like a 1 in 10 year or a 1 in 100 year. They become much more common. And the 1 in 1,000 year flood is over the top of the Thames Barrier. So we would need to invest substantial funds in infrastructure just to protect London. We'd also need to do the same in most of our major cities, most of which lie in low-lying coastal areas. At the moment, we spend £540 million every year on coastal flooding and defences and damage. That value will increase dramatically. If we look at the probability of being flooded with 1 meter sea level rise, this is the number of properties affected by a 1 in 200 year coastal surge, even under 1 meter local sea level rise. So all of these red spots here are floods, properties that would be damaged in a 1 in 200 year flood event. And these black spots in this other graph, these are the defences under risk under 0.5 meters sea level rise. But it's not just sea level rise that we need to be concerned about. We don't live in a country with glaciers, but we have glaciers in lots of other countries, and these glaciers provide water for downstream communities. These glaciers are melting in the dry season and supporting the river flow. That river flow is then used for domestic consumption, for drinking water, for eating and drinking, for industry, for hydropower, and for ecosystem services. If those glaciers go, then we no longer support that downstream melt, and we would lose the buffering that these glaciers give. It would make droughts more likely. So you can see this red line here. This is our baseline runoff. As the glaciers decrease, first of all, we get an increase in meltwater, but then the meltwater decreases as the glaciers get very small and our runoff is lower than it used to be. So this is why it's important to limit global warming to not 2 degrees or 3 degrees, but to less than 1.5 degrees, because at that level, we will retain most of the glaciers in the ice. We need to keep the glaciers, keep the ice in the glaciers. And if we limit warming to less than 1.5 degrees centigrade, we will keep most of the warming. These figures are from the IPCC special report on oceans and the cryosphere that came out in 2019. And I've also taken the figures from the assessment report 6, which has very recently come out. Under 2 degrees of warming, or just under 2 degrees of warming, we'd have 44 centimeters sea level rise by 2100. But under these higher end scenarios, we're looking at 77 centimeters sea level rise by 2100 just from land ice. How close are we to limiting to 1.5 degrees warming? We need to, if this is our global temperatures and this is our timing, we need to follow this green pathway. Okay, we are already past 1 degree of warming. So we've got the pre-industrial era, we're already past 1 degree of warming. We're forecast to pass 1.5 degrees of warming in the year 2040. So we have to do aggressive mitigation now to slow that curve and change its direction. And these are the global emissions and how they need to change if we are to meet this 1.5 degree C objective. Here are CO2 emissions on the y-axis, and here is our time on the x-axis. And these are the pathways that we need to take. You see that the longer we leave it to take aggressive mitigation, the steeper our emissions have to crash. Okay, so we are currently in the year 2020. We need to follow this kind of 2022. We need to kind of follow this like kind of gray line here. Okay, the longer we leave it, the more vertical our decline in global greenhouse gas emissions needs to be. So let's think about what the UK emits in terms of carbon dioxide. These are the UK CO2 emissions from the year 2017. So we have transport and energy, so natural gas, all the different kinds of energy that we have, transport, aeroplanes, cars, trains, and so on, residential, 15%, business, agriculture, and other. So it's really transport, residential, and energy supply that are some of the biggest emitters. And these are the UK's carbon dioxide emissions. They actually peaked in 1973, and they've declined by 38% since 1990, faster than any other major developed country. Here, the red line is our total greenhouse emissions. We've got 1990, and you can see them going down sharply, especially since the Climate Change Act in 2008. So our emissions are coming down. We're doing well. Our emissions are declining. And part of this is because we're changing the energy mix. This is the energy mix from 2019. Over half of our energy is renewable. Then we have nuclear, which is a fairly low carbon, although it maybe has some other issues. And then we have 17.5% from natural gas, which if you've been watching the news, we'll see that is quite an important geopolitical driver at the moment. So we've been changing our mix, and if any of you live near the coast of Essex, you might see the wind farms offshore. We have a fantastic source of energy from the wind in the North Sea, and we are really increasing our energy mix from wind power. Here is the record minimum share of fossil fuels in Britain's energy mix, and you can see that almost every year we've broken our record in terms of how much carbon dioxide we used, or how much fossil fuels we used in our energy mix. So each year we are using less and less energy from fossil fuels. And hopefully over the next few years, we will get to no energy from fossil fuels. One of the other major sources of carbon dioxide is from our food. This graph shows where the carbon dioxide in our food comes from. So we've got the green is the land use change, so going from kind of forestry to pasture or something else. The brown is the farm, and then we've got the red is the transport and the packaging and the processing. And I just want to highlight a couple of things down here. Down at the bottom, we've got nuts, and the land use change of nuts means that they actually have a negative carbon dioxide imprint. And that's because to get nuts, you have to grow trees. So eating peanut butter, good for the environment. And then we have our vegetables and things down here. So we've got things like bananas. You may be worried about eating bananas or your mangoes or something from abroad because you may be worried about the carbon from your transport. But actually, the factors such as transport distance are small compared to the overall food type. So you can eat mangoes or bananas fairly guilt-free, particularly things that have come across on air freight, on ship. They're packed in cold containers and they come across very quite carbon efficient. Then if we move up the graph, we've got things like eggs and fish. You can see that rice produces methane, paddy-farms produces methane, but it's still quite low. Then we move up here and we start getting into things like beef. So here we have beef from a dairy herd. You can see that the brown here is quite significant. We've got lots of methane from beef, lots of methane from lamb and mutton. And at the top, beef herd, an absolutely huge spike in carbon dioxide production from beef. And it's really because these ungulates are beef, are pigs, are sheep. They produce a lot of methane burps, and these methane burps are what's driving a lot of the carbon dioxide production from these animals. So small changes in what we eat can actually have a big impact. If you made beef a special treat to have once every now and again, instead of a midweek staple meal, for example, your annual carbon dioxide imprint would be drastically less. You don't even have to be vegetarian, because you can see that things like chicken and poultry meat, so here's chicken, poultry meat down here, pig meat, sausages, they're actually very low. That's because the non-ruminant livestock do not produce methane and have significantly lower emissions than beef and lamb. So even just a low red meat diet can significantly reduce your carbon footprint. Obviously, a vegetarian diet where you're eating perhaps mostly these vegetables down here would have a much lower carbon footprint than something that's using a lot of animal products. But everybody's diet is different, and we can do what we can, but what we can do is make informed choices about the food we eat. Maybe beef and lamb can be a special treat to enjoy on special occasions. We can also change our travel. Perhaps we can take the train more, perhaps we can walk or cycle or use public transport. Perhaps we can make a flight for a holiday a special treat every few years rather than an annual treat. And we can try and avoid driving short journeys in diesel or petrol-powered cars as much as possible, or perhaps considering switching to electric and having our home on a renewable energies tariff. And we can make our homes more sustainable. Perhaps we can look at how we heat our homes with oil and gas boilers. Perhaps we can drought-proof or put cavity wall insulation. These things mean that we need less energy to heat our homes. Maybe we can buy reused clothes, shop in charity shops instead of buying new. And I'm sure this might be something that Laurie will talk about. Or maybe we can choose a renewable energies tariff. What else can we do? We can educate, communicate, advocate, and demonstrate. And this is something that we're really helping our people to do when they come and study our new degree schemes. We're hoping to make activists and social people driving for social change. So I want you to think about things that you could do. Perhaps you could be vegetarian 4 days a week, or 1 week a month, or go for veganuary. Perhaps you could talk about climate change, or pledge to cycle or walk for journeys less than 3 miles, say. Right, maybe you could dry your clothes outside in the summer months instead of using a tumble dryer, or take a no-plane holiday in the UK. I'm going to Vienna for a conference in a few weeks' time, and I'm going by train. And I have to say, I'm really looking forward to that.